N-channel MOSFET. So the structure of an N-channel MOSFET consists of a P substrate first of all, then on the top of that we will have an insulator, on the top of insulator is usually oxide, say silicon dioxide, and then we have a metal region, so that we call as the gate. So this is bulk, gate, then we will have an N plus region, plus stands for heavily doped region. So this we will take it as source, this side we will take it as drain. Though it is symmetrical, you can interchange source and drain because the structure is very symmetrical with respect to source and drain. N plus stands for heavy doping. Okay, so heavy doping means of the order of 10 raised to 18 or 10 raised to 19 per centimeter cube. Okay, so that it will be highly conductive and you can join with metal and make a good ohmic contact. So that is one purpose. Another purpose for making N plus region is to so whenever we have a PN junction we will have a depletion region. So if I draw that depletion region here, it will be mostly extending to the P substrate. That's because P region has doping concentration of the order of 10 raised to 16. It's not heavy doped, and therefore whenever there is a PN junction between two material, one material is heavily doped and the other is lightly doped, the depletion region will mostly enter into the lightly doped region. Okay, so that is as per the charge neutrality condition. That means the same amount of positive charge and negative charge will be there. So for example, in a PN junction, P region has negatively charged ions and N region has positively charged ion, and if the width of the depletion region in the N region, suppose if it is Xn, then the concentration of charge there, because it is heavily doped, it is going to be equal to Nd, which is of the order of 10 raised to 18 or 10 raised to 19, and this should be equal to the negative charge in the P region. So if the width is say Xp, then this will be Na. Okay, so this will be the charge equivalence at the depletion region. So one side of the junction you have negative immobile charge and the other side you have positive immobile charge. In the case of a PN junction, N plus region will have positive charge. So this is the positive charge per unit area. Okay, positive charge, and this is negative, and they both should be equal. So if Nt is much greater than Na, so as I told you, it is at least 100 or 100 times greater. So then what will happen is that so let's take Nd is 100 times Na. This will give what? This will give rise to Xp is going to be equal to 100 times Xn. Okay, so if you take a Na to this side, you will get 100. So Xp is equal to 100 into Xn. Okay, so That is why when I draw the depletion region, I will only extend the depletion region into this P region. I will not extend it into the N plus region, because in the N plus region the width is going to be so small that it is unnoticeable when you draw in the scale. 1/100th of this distance is practically negligible to be shown explicitly. So that is one thing. So now yesterday I told you that we will take source as a reference, and two potential that we apply. One is called VGS, so that is this voltage. VGS is the gate to source voltage. Source is grounded, and then the other one is VDS. Okay, so this is VDS, that is the drain voltage with respect to a source. Okay, so these are the two most important voltages, and in addition to that we can also think about another voltage, VBS. Okay, that is the voltage at the bulk with respect to source, but usually we connect the bulk to the source. Okay, that means we will ground source also, but in case there is a more negative polarity available in the big circuit that we have, so this MOS will be like part of a big circuit. You can think about that that way, and then if a more negative potential is available in that circuit, the bulk terminal can be connected to that negative. Otherwise we will just connect it to the ground. Okay, so let's assume that we will consider the case where VBS is equal to 0. So bulk terminal voltage also we are saying in reference to the source. So source is like the reference when we discuss the operation of a MOSFET. Okay, so now so how does this work? So in order to see that, so let us consider the case where initially so we will go in step by step the operation. Initially we will consider the case where VDS is equal to 0. Okay, so VDS is equal to 0. That means we are not applying any potential, so it's like just joining the drain and source. Okay, or in other words, you are grounding the drain also. And then what we do is we are going to apply a positive potential at the gate. Okay, so let VDS is equal to 0, and let us vary VGS from 0 to higher positive voltage. Okay, so this is what we are purpose to do. So we apply VDS equal to 0, and then we are increasing the value of VGS from 0 to higher voltage. So then what happens? This is something that we have already studied in the with reference to MOS capacitor, because if VDS is 0 and then we are applying VGS means so it is something like applying a VGB, because source and bulk are at the same potential. So when you increase the gate voltage, it will just function like a bulk. So initially what happens, as VGS increases, the holes which are underneath the oxide, they will be repelled away, and that way there will be a depletion region that will be created. Okay, so this is the depletion region that will be created. So we have a depletion region which extends from source to drain. Okay, so which is which has no carrier in between. Okay, so there is no conduction possible, there is no channel yet. So this is for smaller VGS voltage that we apply. Now as we increase the value of VGS, at some point of time what will happen is that our depletion region will keep on extending and there is a maximum depletion region width we discussed in the last class, beyond which the depletion region will not extend. But then what will happen is we will have some electron created in the interface. Okay, there is a channel that is gets created at the interface. Just underneath the oxide we will have a layer of electrons, and the concentration of that electron is going to become larger than the concentration of the Na, which is the acceptor impurity concentration. So that is what we call a strong inversion. Okay, so once the strong inversion happens, so what is the condition for strong inversion? When VGS become greater than VTH. So we define what is called as threshold voltage, then we will have strong inversion. Okay, and a layer of negative charge, that is these are not ions, these are basically electrons. Okay, strong inversion means electron will form a layer underneath the oxide region. So that is what I am denoting here. So from left to right you have a channel that is created. So, and this will basically connect the source region to the drain region, N plus source region, and to the N plus drain region you have now a path which is full of electrons, and therefore you can treat now this this layer from source to drain. Because of this availability of mobile carriers which are electrons, you can think of it as a conductor. Okay, so if it is a conductor, then it will have some conductivity or resistivity. So you can think about it as a conductor, and then if you now apply on the top of this condition, if you apply now a non-zero VDS, then current can flow because there is a path for electron to flow from source to drain. So if you apply a positive potential in the drain, then the electrons are going to flow from source to drain, and therefore the name source. Okay, source supplies the carriers for the flow of current, and drain is the point at which it comes out or it drain out. Okay, so it is supplied by the source and it is drained out at the drain terminal. So therefore the name. Now if I reverse the polarity of the VDS, then the source will be the N plus region in the right side and the drain will be on the left side. Okay, so it depends upon the polarity that you apply. You can always put the NMOS in either fashion, upside down, or here it is like as I have shown S, I have defined for the left, so that should be the lower polarity compared to the drain. Okay, if I want to keep the source at the right side, then you give the ground at the right side point, and then automatically the other side become drain, because source will the point, the terminal from which the electrons are going to be coming from, and they will be draining out at the drain point. Okay, so this I hope it is clear so far. If VDS is equal to 0, as we increase VGS, initially there will be only depletion layer connecting from the N plus source region to the N plus drain region, and there are no mobile carriers. But when VGS become greater than VTH, then we will have an inversion taking place, strong inversion taking place, and that is because of the availability of mobile carriers from left to right, which forms the channel. Okay, so after the strong inversion happens, so mobile carriers create a channel. Okay, the length of the channel is usually denoted by L. The length of this channel is usually denoted by L. Now the MOSFET also has a it's a 3D structure. So if I actually show that also, so there is a width also. So width is basically it is actually into the drawing. Okay, it is perpendicular to the cross section that I have shown here. So that width is usually taken as W. So that is another very important parameter of any MOSFET. Okay, and L and W are something that we will see plays a very important role whenever we design MOSFET based digital circuits. Okay, so this is one thing. And now another thing I can show you is that if VGS is equal to 0, okay, so earlier I kept VDS 0 and then I varied VGS from 0 to higher positive voltage. Now if VGS is kept 0 and I apply VDS, okay, so VDS I apply positive VDS greater than 0, okay, it starts from 0 and it goes upward. Then what happens? So if you look at again the schematic diagram, nothing much interesting happens in that case. That's the reason is because you have a P region which is between the N plus 3. So if I draw just the semiconductor part, you have this N plus region here, another N plus region here, and there is a depletion region which is surrounding this N plus region like this. Okay, and this is a P region. Okay, and you have N plus region. So you can model this like two diodes, two PN junction. Okay, so here you have the diode will be like this, and on the other side you have a diode like this. So this is like the equivalent circuit, and you are basically applying a voltage like this. So this is your VDS. So if you apply a voltage like this, you can see that this diode is getting forward biased, but this is getting reverse biased. And the equivalent circuit is that whenever we have two diode which is connected back to back like this, then one diode which is getting reverse biased will be an open circuit. The one that is getting forward bias can be replaced with a closed switch. So here you have a forward bias diode which can be modeled as a closed switch, but the other diode is like an open switch. So current can never flow. No matter what VDS you apply, current can never flow because there is no path for current to flow. Okay, so to create the path we need to apply VGS. Okay, so only when VGS is greater than VTH, then only the inversion layer which connects the N plus region will create a path for electron to flow. So that is the case, the most important case, which so if VGS is equal to 0, you can say that there cannot be any current from drain to source. So drain to source you can replace it like an open circuit. But if VGS is greater than VTH and VDS is greater than 0, so this is the case where you have a channel existing from drain to source, and as a result current can flow. So let us now look at what is going to be the magnitude of that current. So in order to derive that, so we need to again look at the structure in more detail. So let me draw it again. So you have N plus here, another N plus here, we have oxide here, then we have gate here. So as I told, now I am applying VG S greater than VTH. Okay, so this voltage VGS is greater than VTH, and then on the top of that I am also applying VDS. Okay, so VGS will create a channel, and then VDS will give a voltage across the channel so that current can flow. So the picture is, now we have a lot of electrons here. Okay, so this I am going to show the inversion layer like this. This is the inversion layer, and beyond that I have a negative immobile charges. This is my depletion region. Okay, so the depletion region extends everywhere. Here also it will be there. Okay, now since let's assume that we are grounding the bulk, okay, like this, we are grounding the bulk. So if you look at the PN junction on the drain side, since I have applied a VDS which is positive, so this is greater than 0, because of that the depletion region width is going to become larger this side compared to this side. Okay, so the depletion region width will increase to this side. Okay, so why it is? Because we have a large potential difference between N plus, or you can say that this N plus is given positive voltage, so this is P, which is given ground or 0 voltage. So whereas here both side it is ground. Okay, because a source is the reference, so we are grounding that. So N plus is grounded and P is also grounded, so it is like the depletion region that will be formed with a 0 bias voltage. Okay, but on the other hand you have a reverse bias coming at the drain region, so the depletion region width is going to be larger on the drain side compared to the source side. Okay, and since VGS is greater than VTH, you have a inversion layer and a lot of negative charges, which are electrons, on the top of this depletion region that I have shown here. Now what is going to happen is that when you apply potentials, as I have told here, the inversion layer will have some amount of charge, and let me denote that charge as say Qi. So Qi is the inversion charge density. Density means per unit area. Okay, per unit area. Okay, so if I look at from above, okay, so this is just a cross section, but if you look from above and consider a unit area, in that area you have Qi amount of inversion. I am talking about the electrons, okay, in the channel that has come, okay, because we have applied VGS greater than VTH. Mobile charges will come, which are electrons, and the density of that charge is what I call as inversion charge or inversion charge density. Now this is going to be depending upon what? So Qi, I can give an expression for Qi, is basically equal to Cox into VGS minus VTH. Okay, so you need to understand this expression. So where Cox is also a capacitance per unit, it's an oxide capacitance which we have seen. So there is an oxide here, and therefore there is an oxide capacitance. So you can think about it like a capacitor, and why it is VGS minus VTH? That's because until we rise VGS to VTH, we don't have any inversion layer. Inversion layer starts only after we increase the gate voltage above VTH. Okay, so if VGS is less than VTH, there is no inversion layer, only depletion region will be there with some width which will keep on extending. But we have studied that in depth with the help of energy band diagram earlier classes, that when we increase the VGS value greater than, okay, earlier I said about VGB, but here since bulk and source are at the same potential, I can say in terms of VGS also. So as long as VGS is less than VTH, there is no inversion layer, and therefore there is no point in talking about inversion charge density. The electron concentration are much lesser than the Na, or the immobile charge density in the depletion region. But that will become significant only when we get into the strong inversion region. So in the strong inversion, what will happen when you increase the VGS value above VTH? The electrons are going to be suddenly increasing, okay, and as a result, the depletion region which was extending earlier will not extend further, and similarly the surface potential of the semiconductor will not change, because that is actually depending upon the depletion region charges. But the depletion region charge as well as its depth, that is not going to change. So what is going to happen after or in the strong inversion region or strong inversion mode is it will only increase the charge of electrons in the inversion layer. And so now you can think about it like a capacitor. And the capacitance is basically the oxide capacitance, and the voltage which will bring the charge is VGS minus VTH. So inversion charge is going to be equal to Cox into VGS minus VTH. Now if I consider a small strip, okay, so let me consider a small strip here. Okay, I'm going to denote it as this one, okay, and of width some dx. Okay, so to show it explicitly, I will mark it dx. So if I consider a small strip dx, then okay, so this is the inversion layer charge when your VDS is equal to 0. Okay, now if I consider the case where VDS is also there, that voltage will also be reflected in the channel. Okay, so if you look at the channel voltage, on the left side you have ground, that is on the source side we have ground. So this is the source side, this is my x direction, the length of the channel I am taking it as the x direction, and I am talking or plotting the voltage as a function of x along the channel. What is the potential? On the left side we have 0 because it is grounded. On the right side, say at say L, I have VD. Okay, so this is my VDS. And since I already told you, after you create the channel, if you apply a VDS which is greater than 0, that VDS will be dropped across the channel because it is like a resistance. So if you have a resistance across which you apply a potential, the potential on the length of the resistance is going to increase linearly. Like you are familiar with rheostat, for example. Okay, so it's a long resistance. So as you go along the length of that resistance, what will happen from one end to the other side? One end it will be 0, the other end you will have the full potential. But in between any point, if you talk about the potential there, it will be linearly varying with respect to the distance. So V of x, that is the channel potential. So V of x is called the channel potential. Potential in the channel varies with the function of x. That's because we have not only created the channel, we have applied a potential across it. So therefore this potential is going to vary from left to right. It will increase from left to right. So this is the channel potential. So if we consider a dx width inside the channel, and if you want to talk about what is going to be the inversion charge in that dx region, then we can call it as say dq. Okay, so let me call it as dq. So what is dq? dqi is basically the inversion charge, or inversion charge in that portion called dx. Okay, so that is going to be what? That is going to be this inversion qi, inversion charge qi into, so this okay, before that I want to also bring in the effect of VDS. So here I have written an expression which is the case for VDS equal to 0. So now if I apply a potential, there is going to be a channel potential also I need to take into account. So when channel potential is there, I need to modify this equation. So this is going to become VGS minus VTH minus V. Okay, so this is when you change the channel potential from 0. Earlier channel potential was 0 because VDS was 0 after creating the channel, but now when you have introduced a VDS, the channel, depending upon where you stand at that point, you have different channel potential, and therefore the voltage across the oxide layer is not just which will create the inversion layer, is not just VGS minus VTH, but VGS minus VTH minus V of x. Okay, if it on the left side, it will be VGS minus VTH, because so that decides how much is the inversion charge. But on the right side, we will have lesser inversion charge because the channel potential is increasing, and as a result, the difference between VGS minus VTH and the channel. So it's, you look at it as a capacitor. So if I increase the voltage on one side of the capacitor, then what will happen? The voltage across the capacitor will be reduced by that amount. Okay, so if it was 0 on one side, whatever is VGS minus VTH, that will decide the inversion charge. But right now it is VGS minus VTH minus V, which is the channel potential. Okay, so now I can consider a small infinitesimal distance dx, and then find out what is going to be the charge in that region. So dq or dqi So we are considering a strip which is at x distance from the source region, and we are going to write the amount of charge in a volume. What is the volume of the strip? The volume of the strip is basically W into dx. So W is basically the orthogonal direction to the cross section that we are considering. So that is a depth, okay, and dx is the strip that we are considering. So the amount of charge in a volume, W into dx, located at a distance x. Okay, so that dq, amount of inversion charge, okay, inversion charge. So we are talking only about the charge of electron, not the bulk charge or the depletion charge. So dqi is what? It's going to be equal to the charge density at that point multiplied by W into dx. So what was the charge density? Cox into VGS minus VTH is what the point at which charge begins to be formed, then minus V of x. Okay, so this is going to be okay, so this multiplied by the volume. Okay, so this much was our charge density. Charge density, if you multiply it with volume, we will have the total charge inside that strip of width dx. Okay, now we are interested in finding the current expression. Okay, now therefore the channel current, how do you find channel current? If you have a strip with a charge like this, we only need to find out how fast this charge is moving in time. Okay, so or in other words, we can call that current as ID, which is drain current, usually it is called, is equal to dqi. This inversion charge, they are mobile charges, so they can result in current, unlike the bulk charges which are due to the immobile acceptor ions. So dqi by dt. Okay, so the channel current dqi by dt. So dq is here, so Cox, W I am taking to this side, and then VGS minus VTH minus V of x into dx by dt. So dx by dt looks like velocity. So we are applying a potential VDS and creating these mobile charges to move. So it's like a conductor. So the channel you can think about like a conductor, and you are applying a potential, and these free electrons which are in the channel, they are going to move. They are going to move with a speed which is usually called as the drift velocity. Now drift velocity is appearing because of the electric field there. So there is a relationship between drift velocity and so drift velocity, we can write it as say Vd, which is here it is defined as dx by dt, is basically equal to a quantity called mobility of electron into the electric field. Okay, so this is mobility of electron multiplied by electric field. That means as you increase the electric field, that is how any conductor current flows. So when you apply an electric field, basically the electrons will get accelerated and move with the speed, and so the proportional constant is what we refer as mobility. Okay, so usually the mobility of electron is going to be in the opposite, I mean the electrons are going to move in the opposite direction, because the current is going to be from say drain to source, and the electrons are going to move from source to drain. So this is the electric field. Okay, so I can substitute this as so this velocity, drift velocity, I can write it as mobility, a constant, multiplied by electric field. Again, so what is this electric field? Okay, how much is going to be the electric field? So electric field is basically the slope of potential variation, right? So earlier I have drawn the channel potential. It is varying. I am approximated it with a linear line from left to right. It is increasing like this. So electric field is basically the slope of this, or dV by minus dV by dx is what we call as electric field. So I can write in that manner. So I can write it as so at that location where we have an electric field is at location Ex. So this is going to be equal to, or let me write it below. So this I can also write it as mu n into d v of x by dt. Okay, so minus with a minus sign. Okay, so this is going to be equal to dv of x by dt. Okay, so okay, another thing I should have already included is the inversion charge is going to be negative because they are electrons, so I need to give a minus sign here, Cox into Vg. Yeah, it's a negative charge, so I need to put this negative sign here everywhere. Okay, so this is negative, so this is going to be negative, and what does that mean? This negative charge, so minus dx by dt, I am going to so that is going to be the velocity of electron. So dx by dt is basically the velocity of electron. Now velocity of electron in response to the electric field will be also in the negative direction, so there will be a minus here, and so this will cancel with this minus sign. Okay, so now so we will check the sign more properly after we finish this derivation. So far I hope you are with me. So we have defined dx by dt as the drift velocity, and drift velocity is going to be in the opposite direction of the electric field. Electric field is from right to left. This is the direction of electric field, from drain to source. Okay, there is an electric field, and the electrons are going to move in the opposite direction. This is the direction of drift velocity. Okay, so dx by dt. Okay, so all right. Okay, then what is going to happen is, so now let's substitute this back into our dx by dt here. So therefore id is going to be equal to minus Cox W Vgs minus Vth minus V of x into what is here, mu n into dV of x by dt. Sorry, this is dx, sorry, gradient of potential is not dt. Dt means time change. So electric field is basically equal to minus del V, right? So del is basically dou by dou x, so that is dV of x, capital V, by dx. Okay, so it is dx here. So we are almost reaching there. Now I take this dx to the other side. It's basically solving differential equation. We take one variable to variable separable form it is. So this is equal to Cox W Vgs minus Vth minus V of x into, so I can put mu also here, minus mu n Cox W, and then there is dV of x. So the variable on the left is x, the variable on the right is dV or V of x. So now I can integrate this, integrating on both sides. So the current has to be constant with respect to x, because when a current flows in x direction, any cross section you take, it is the same current. So current should not vary along x, otherwise something I mean that doesn't satisfy the continuity equation. The current through a channel, if it is flowing, okay, any place you take, it has to be the same current. Okay, so here also it should be I, here also it should be I. There should be no change. So ID is a constant of x. With respect to x, ID doesn't change, and therefore when you integrate, you can take ID outside, and you are integrating from 0 to L dx, and then similarly minus mu n Cox W, then here VGS minus, so one term here, the voltage is going to change from 0 to VDS, so VGS minus VTH into dV of x, so that is one term, and the other term is basically minus V of x dV of x. Okay, so I can put one more term here, 0 to VDS. Okay, so this integral is simple integral ID into L. Basically you will get integral of dx is x, and then you will get L, and here I will get what, minus mu n Cox W. So I have two terms. So here the first term is basically VGS minus VTH is constant with respect to dV, V of x. So here I will have V of x, and this V of x is from 0 to VDS, then minus, here I will get integral of V of x dvx is basically V of x square by 2. Again the limits are from 0 to VDS, so that is mu n. Okay, so I will take this L to the other side, therefore I can write it as ID is equal to mu n Cox W by L, and here I will have VGS minus VTH, so if I put the upper limit, it is going to be VDS, then minus VDS square by 2. So this is my current expression. Okay, so I have assumed my current as going from left to right. Okay, but actual direction of the current is in the decreasing direction of these. Okay, so I have assumed that the current is going from left to right, but actually the current is from right to left, right? Because we are applying positive voltage at the drain and negative voltage in the source. So the actual direction of current is not in the positive x direction, it is in the negative x direction. So that is why there is a negative sign. So you can so it depends upon how you take the direction of the current. So if I take my current direction as this way, okay, so if I define it as this way, then my current is going to be in the negative, I will get it as positive. So we can drop this sign for that reason and take the current direction as into the drain terminal. So therefore, so drain current or drain to source current IDS is equal to mu n Cox W by L into VGS minus VTH into VDS minus VDS square by 2. Now you can see that there are two terms here. One is basically a linear term with respect to VDS, and the other is basically a parabolic term with respect to VDS with a negative sign. Now for small values of voltages, you can neglect, so if VDS is very small, then we may neglect the contribution from the square term. VD is this term. Okay, so we will have something like an Ohm's law. So therefore IDS is basically mu n Cox W by L VGS minus VTH. Okay, so this you can think about like a conductance. Okay, so you can think about, so for small VDS values, so this you can think about like the one inverse of resistance of the channel. Okay, so where RC is called the resistance. Okay, it's like an Ohm's law, like VDS is equal to IDS into RC, channel resistance. Okay, so this is channel resistance. So that is applicable only in the case of low values of VDS. But as VDS increases, what will happen? The second term become prominent, and therefore we cannot neglect it, and as a result we need to take into account of both terms at the same time. So if I draw these characteristics as a function of VDS, so this is our VDS. So for small means say to some level we can assume that VDS is small, and at that time the current IDS is going to be linearly proportional to VDS. So that means it will go like a straight line. Okay, but then after that the second term become prominent, so we need to take into account of the full equation where there is a minus VDS square by, so the second term is going to reduce the increase. So that means it was supposed to go like this as a straight line, but then it will come and as the voltage increases, that term is going to become more and more prominent. At some point of time, what is going to happen is that the two terms are such that the increment is going to become 0. Okay, so at some point of time, if you take the derivative of IDS, it is going to become 0 with respect to VDS, and that point onwards, if you increase further, then the current is going to go down, because the second term is going to dominate more than the first term, and as a result you will have a decrease in current. But that can never happen practically, and as a result what actually happens is from then onwards the current will remain constant. Okay, so we have 3 regions for the characteristics. So one is basically the linear region, second, so that is this, and the region between say origin and point 1 is called linear region. Then we have quadratic region, and after that we have what is called a saturation region. So we will continue our discussion in the next class from here onwards. So